Yeah, Team 16, and project is on analysis and the redesign of a hairdryer. The hairdryer helps dry and style hair by blowing air at different rates and temperatures. It has an electric fan that blows air across a heating coil. This shows the components of a hairdryer in an exploded view. We'll be manufacturing 50,000 units for our primary customers who are household users and 20,000 units for our secondary customers for professional use and salons. As seen on the fast diagram, all these sub-functions complement the main purpose of a hairdryer, which is to dry or style hair. Our hairdryer can be assembled in two ways. That is assembly sequence 1, which is top-down, and assembly sequence 2, which is bottom-up. There is a slight preference for sequence 2 over sequence 1 because sequence 2 allows better transfer and handling, ease of testing sub-assemblies, and ease of assembling in parallel. The function component mapping matrix highlights the functions as set out in the first diagram of all the components of the hairdryer.
The quad chart was used to distinguish between high and low functional importance and manufacturing/assembly cost. The redesign focused on the front enclosure due to the high cost and the heater ribs and zigzag wire assembly due to their high cost and high functional importance. Our primary variant is for the individual or home user, and the secondary variant is for the salon chain employee. The primary variant has a smaller button, a 2-setting speed control knob, a 2-setting heater control knob, and a sliding on-off button. The secondary variant has a large motor for enhanced durability and to provide the larger air volume that is needed in a salon setting. It has 3-setting speed and heater control knobs and an on-off push button. Most hairdryer assemblies start with the motor assembly, but this would cause 2 unique variants for the entire assembly sequence. Delayed differentiation will allow the common components to be assembled up to the point of the on-off button, heater knob, and speed control knob, which are unique. The motor housing and fan that are common would then be assembled, followed by the unique motor. The common heater rib, zigzag wire, front neck cover, heat shield, and front enclosure would finish the assembly. The functional differentiation that are the same for both models are supply electricity, add heat, stabilize temperature, maintain airflow, minimize noise, and reduce vibration. Differences are set speed and adjust temperature. Most of the hairdryer components are common between the customer variants, but the differences are the heater knob, speed control knob, and the on-off button, and the motor.
Here is the manual assembly analysis. It takes around 126 seconds to assemble the product with the assembly efficiency of 23.82%. The enclosures are major time-consuming platform parts, and on-off switch is a module component with higher assembly time. Thus, to improve the assembly, enclosure was redesigned, the idea being to reduce the number of parts and the variety, have assembly in single direction without involving orientation change, and avoid use of fasteners. Quad chart also represents it as higher assembly cost part. The guidelines of reduction in part count, variety, and fasteners are used here. The on-off button was selected as a module part. The lower manufacturing cost can be attributed to its size, but has higher functional importance and assembly cost. It was redesigned by adding a flat edge to facilitate orientation, snap fit, and chamfers for easy insertion. The button is needed when we need to supply power for use, thus having a higher functional importance. The guidelines that inspired these changes were preference to snap fits, addition of features to facilitate orientation, and easy insertion. Hence, the assembly time reduced to about 94 seconds with an improved manual efficiency of 31.96%. The redesigned parts still serve their functions without any modifications. Having a larger size, the cost for enclosure manufacturing of individual enclosure might go up, and it may cost extra to put features on the on-off switch.
The heater ribs and zigzag wire platform subassembly was selected for redesign due to the high assembly costs and high functional importance per the quad chart. The high insertion costs are due to the 3 heater ribs that need to be held down during assembly to maintain the orientation, and the high relative handling cost due to the lack of symmetry for the 3 heater ribs. The heater ribs also have resistance to insertion. The redesign reduced the 3 heater ribs to 2 based on DFA1 reduced part counts. The original zigzag wire was open loop so it would tangle. It was changed to a closed loop design based on DFA8, avoid tangling and nesting. The heater ribs were not symmetrical, so the second heater rib was made symmetrical based on DFA6, increased part symmetry. The heater ribs were difficult to orientate, so the slot was updated in the first heater rib based on DFA7, add features to facilitate orientation. Before the redesign, the total handling cost was $1.62 and the total assembly cost was $15.42. After the redesign, the total handling cost is $1.17 and the total assembly cost is $6.93.
Coming to the process selection, the two parts that are chosen are the enclosure and the heater rib. Referring to the function component mapping matrix, the width of the dryer inner cavity is critical for ensuring good airflow and also for minimizing the noise. The tolerance is plus or minus 0.2 mm and the surface finish is opaque high gloss. Coming to the heater rib, the dimensions of the slot are critical for ensuring proper insertion of the perpendicular heater rib. This ensures that there is proper addition of heat and also there is proper stability of the temperature at a particular heat setting. For the heater rib, considering the mass as 11 grams, thickness as 2 mm, and tolerance as 0.25 mm at an economic batch size of 50,000 parts, sheet metal working is the best manufacturing process. For the enclosure, considering the mass as 150 grams, thickness as 3 mm, and a tight tolerance of plus or minus 0.25 mm with a surface finish that is opaque and high gloss, injection molding manufacturing process is the best for an economic batch size of 50,000 parts.
Here is the injection molding cost calculation for enclosure. The assumptions were ABS as the material, single cavity mold, high gloss, opaque finish, and 0.5 mm silver approximate tolerance, and using side pulls for rear venting holes. The cost comes out to be around $8 per part, with mold cost being the highest. We checked the part using DfM Pro and got two feedbacks, inclusion of draft angles and reduction of undercuts. Thus, we remove the side pull requirement by aligning the holes in pull direction, incorporating draft angle, and reduce thickness from 3 to 2 millimeters. The design guidelines of avoid side pulls, minimize wall thickness, and add draft angles help bringing up these changes. This leads to a significant reduction in the operating and mold cost, while reducing the amount of material used. Product functionality stays intact and doesn't bring significant changes to assembly cost, since the interior portion hasn't changed.
Design for seat metal has been carried out for the heater rib. We selected aluminum 1100 grade seat for the heater rib due to its promising thermal property and resistance to corrosion. Pre-DFSM process of heater rib initially involved blanking of the part followed by a punch in the mid. Initial heater rib design includes sharp corners, non-standard punch, and narrow features. The total estimated cost including material, operating, and die cost is $0.21 per part, estimated for a batch size of 50,000 parts. We implemented 3 DFSM considerations in the redesign of heater rib, which include rounded corners, a standard punch in the mid, and increasing the width of narrow features. The estimated cost for redesign heater rib is $0.211 per part. The material cost is slightly increased in this case due to increased width of narrow features. Cost analysis carried out in the hub provided $0.124 per part for pre-DFSM and $0.114 per part for post-DFSM. The estimated cost is 80% of the hub's quoted price. Table shows the comparison between cost evaluated using analytical method and the hubs. The hubs costs are different than the analytical because hubs uses more efficient and advanced technology based on updated data, whereas analytical approach is based on some static assumptions. Also, extrapolated price of the hubs are approximated price per part based on the batch size.
As a service addition to our hair dryers, we will add online product registration, which can be done using serial numbers and QR codes. The registration will be free of cost with warranty extension, accessories, and styling tutorials available as add-ons with their respective costs. We, as the manufacturers, will provide the part replacement and recycling services to reuse and recycle as much as possible from used dryers instead of sending the worn products to trash. Accessories are sold separately to minimize the material and energy consumption since not everyone may require an additional component. Concluding, we see that the time and cost benefits for our manufacturing and assembly processes are possible by following the DFA and DFM guidelines. The pros of the design include easy unidirectional assembly, reduced number of parts, and yearly reduction in cost of enclosures and heater automated subassembly by $466,000. However, since the number of heater ribs are reduced and there are changes in the effective area over which air flows, the efficiency of drying operation can reduce. Hence, if we were to start over, the flow simulation and optimization softwares can be utilized along with the design guidelines to help improve the manufacturing and reduce costs while maintaining the flow efficiency. Thank you.